Today we're going to introduce Ampere's circuital law. The last thing we did was apply the Biot-Savart law to an infinite line of current. Here we have the infinite line of current with the current coming up out of the page. We found that the magnetic field intensities were circles around that wire and with the magnetic field intensity in the counterclockwise direction, or in the A sub phi direction. So with the wire lying along the z-axis, we found that the magnetic field intensity was equal to the magnitude of the current flowing through the wire over 2 pi rho, and it was in the A sub phi direction. And we can show qualitative agreement with this result from an experiment where we have an infinite line of current going through a piece of plastic where we've placed iron filings. When current is flowing through the wire, we see that the iron filings rotate along the field lines and form these concentric circles. Farther away from the wire, we see that the iron filings have not moved, and that's because of the fall off in the magnetic field intensity with distance from the wire. Let me form a path that encloses the wire. And what we're going to do is integrate H dot dl around this closed path that encloses the wire. And this arrow here will indicate the direction of integration. So it's going to be kind of in the phi direction to go all the way around the path. So let's substitute for H our known magnetic field intensity for our infinite wire, and for dl, let's put the dl in for cylindrical coordinates. So A phi dot A rho is 0. A phi dot A phi is 1, so that leaves us with I over 2 pi rho d phi, and A phi dot AZ is 0. So the rows will cancel, and we will be left with the integral of I over 2 pi d phi, and so we're only integrating with respect to phi, so to go completely around our closed path, we'll go from 0 to 2 pi. So we can take the I over 2 pi out of the integral, so we'll have an I over 2 pi. So when we integrate d phi, we'll get phi, and we're going to evaluate that between 0 and 2 pi. So we have I over 2 pi times 2 pi minus 0, or I. So for any path we pick where the closed path encloses the wire, the integral of H dot dl will equal the current flowing through the wire. Now we're going to look at the integral of H dot dl around a closed path that does not contain our current carrying wire. So let's look at this particular path where we go from A to B to C to D and back to A. And A will be at location rho 1 phi 1 z, B at location rho 2 phi 1 z, C at location rho 2 phi 2 z, and D at location rho 1 phi 1 z. So this particular path of integration is in the same plane because A, B, C, and D all have the same z values, but we'll quickly see that it wouldn't matter if these z values were different. So again, I've substituted our value of h and our value of dl for cylindrical coordinates. So a phi dot a rho is 0, a phi dot a phi is 1, and a phi dot az is 0. So that's going to leave us with the integral of I over 2 pi rho d phi. Since a phi dot a rho is 0, there's no contribution when we integrate in the rho direction, and since a phi dot az is 0, there's no contribution when we integrate in the z direction. So the rho and z coordinates of the points will not matter. So these rho's will cancel. We can factor the I over 2 pi out of the integral, so we're just left with the integral of d phi. So when we integrate from a to b, phi will go from phi 1 to phi 1. When we integrate from b to c, phi will go from phi 1 to phi 2. When we integrate from c to d, phi will go from phi 2 to phi 2. And when we integrate from d back to a, phi will go from phi 2 to phi 1. The integral from phi 1 to phi 1 of d phi is 0, and the integral from phi 2 to phi 2 of d phi is 0. So we have an I over 2 pi. We integrate d phi and evaluate it between phi 1 and phi 2 for this integral. And for this integral, we have phi evaluated between phi 2 and phi 1. So we have I over 2 pi times phi 2 minus phi 1 plus phi 1 minus phi 2. So that's I over 2 pi times 0, or 0. So the integral of h dot dl around this path that does not enclose the wire is 0, and I think you can see that this would be true no matter what path we chose. So even if the path looks something like this, the integral of h dot dl around that path would be 0 because you only get contributions when you're moving in the phi direction, and since we go around a complete closed path, those contributions will cancel. This can be stated as a fundamental law, our third Maxwell's equation, Ampere's circuital law. So the integral of h dot dl around a closed path is going to equal the current enclosed by that path. We will use a right-hand rule to interpret this equation. So if you put your fingers of your right hand in the direction of the integral of this closed path of the integral of h dot dl, if you get a positive result, the current is flowing in the direction of your right thumb. If the result were negative, then the current would be flowing in the opposite direction of your right thumb. We now have the integral form of Ampere's circuital law, which we've added to our previous Gauss's law in integral and point form and the conservative nature of the electrostatic field in integral form to our list of Maxwell's equations for static, electric, and magnetic fields. We'll shortly find the point form of Ampere's circuital law, which will allow us to obtain the point form of the conservative nature of the electrostatic field. Let's look at some currents and paths to figure out how to interpret Ampere's circuital law. Let's look at path C1 for our path of integration, and let me define the direction with that little arrow, and let I1 equal 3 amps. So put the fingers of your right hand in the direction of C1. That's the direction of our integral of h dot dl. And your thumb then points in the direction of the current, which we'll see as 3 amps. So the integral of h dot dl around C1 in this direction is 3 amps. Now let's define a path which I'll call minus C1. So we're integrating now around our path C1 in this direction. So in this case, the integral of h dot dl, you put the fingers of your right hand in the direction of minus C1. So your thumb then points down to the lower left along this path. So the integral now will equal minus 3 amps. Now let's look at path C2. So you're going to integrate h dot dl in the direction of C2 here like this. So your right thumb points to the upper right, and you see you have, let's define again, I2 as being 3 amps. So you have 3 amps flowing in this direction through the path and 3 amps flowing in this direction through the path. So those currents sum to 0. So the integral of h dot dl is going to be 0 for around path C sub 2. Now let's look at path C3. And again, let I3 be 3 amps. Okay, so you do the integral of h dot dl, putting your right fingers in the direction of C3, and your thumb is going to now point in the direction of current flowing through your path here. But notice that the current doesn't flow through this surface, it flows behind it, so there's no current flowing through, so the integral in this case is going to be 0. So we've been applying Ampere's circuital law, and we've been thinking of the area defined by the path as these taunt surfaces as shown here. So in the case of the integral around C1, we see that our wire punctures our path once, so we have 3 amps flowing up to the upper right side like this. In the case of path C2, our wire punctures our area defined by the path here, this taunt surface, with 3 amps going in one direction and 3 amps going in the other, so the sum is 0. And finally, for contour C3, our wire goes behind and never punctures the area, and that's why the enclosed current was 0 in this case. It turns out you can use any surface area that is defined by your path of integration. The surface area doesn't have to be a taunt surface as shown in these 3 figures here. So in other words, your surfaces could be surfaces as shown in these 3 figures. So you can think of the surfaces like a bag where the opening to the bag is your path of integration. So in the case of A here, with a long straight wire, it will puncture the surface shown in figure 4.4 up here, and also the surface, which could be like a bag, shown in figure 4.5a here. Similarly, in part B of this figure, in this case, the wire will puncture the taunt surface twice, so you have no current flowing through it. In this case, the wire goes into the bag and back out without ever puncturing the surface. So again, you have zero current flowing through your surface area in both cases. Finally, in this last case, with the taunt surface, the wire never went through the surface area we have here defined by our path of integration. But in this case, the wire can puncture the bag twice and you have no current because you have 3 amps going in and 3 amps coming out, so you have no net current going through the surface area defined in this case, where you think of the surface as being a bag and the contour of integration, your path of integration, being around the opening of the bag. Here's a wire that's infinitely long, and we're looking at a cross-section through it. And let's say there's 4 amps flowing into the page, uniformly distributed across the cross-section of the wire. I've defined a path of integration that goes completely around the wire, and we're going to integrate in the clockwise direction. So if you put the fingers of your right hand in the direction of the integration, your thumb points into the page. There's 4 amps flowing into the page, so this integration will give us 4 amps. Now I've defined another path that completely encloses the wire, but now we're going to integrate in the counterclockwise direction. So with your fingers of your right hand in the direction of the integration, your thumb points out of the page, which is the opposite direction of the current flowing. So the integral of H dot dl around this path will give us minus 4 amps. Now I've chosen a path that goes clockwise, but it cuts through the middle of the wire. So only half the current is flowing through the surface here. So if you put the fingers of your right hand in the direction of integration, your thumb points into the page, and the amount of current flowing into the page through this surface is 2 amps. So this integration around that path will equal, of H dot dl will equal 2 amps. When we are applying Ampere's circuital law and we have these paths of integration as shown in this figure here, we are going to refer to those paths of integration as Amperian loops.